So this is section 4.3, which is all about right triangle trigonometry. I do have a video that connects right triangles to the unit circle. So some of the things in that video I'm going to go over again in this video, but all of the examples are different than what's in that video. I made sure to have different numbers so that way you get more variety, more examples. So I'm going to start with the 6 trig functions. And these all come from a right triangle. And so we have our angle as theta. So that's a Greek symbol, theta. And the side that's basically touching or next to that is considered the adjacent side. And then we've got the side that's across from that as the opposite. And then, of course, the side that's opposite the right angle is called the hypotenuse. So we label everything in terms of adjacent, hypotenuse, and opposite. And so we usually just abbreviate them with the first 3 letters. And so the sign of an angle is opposite over hypotenuse, and that's where we get the abbreviation SO. So you may have heard SOHCAHTOA, and that comes from the S for sine is the opposite over hypotenuse. And then CA deals with the cosine, and so that's adjacent over hypotenuse. And then tangent is for TOA. TOA is tangent, which is opposite over adjacent. And so the 3 main trig functions we have are sine, cosine, and tangent. And SOHCAHTOA helps you remember how you get the value, or it's a ratio of 2 sides out of a right triangle. The other 3 trig functions are basically the reciprocals of these main 3 trig functions. So we have cosecant. So I'm actually going to, so cosecant is abbreviated CSC. And so that is 1 over sine. Then we have secant, which is 1 over cosine, and then we have cotangent, which is 1 over tangent. And since they're the reciprocals, it's basically the opposite of the ratio that they're kind of the reciprocal of. So like sine is opposite over hypotenuse, so cosecant is hypotenuse over opposite. Now, the way that I remember which trig function is which reciprocal is sine needs to have a co with it, so that gives me cosecant. Cosine has a co, so then secant is the choice that goes with that. And then we have tangent and then cotangent. The tangent and cotangent makes sense. I don't know who decided to name these, that decided to make sine and cosine not reciprocals, because that would make sense. Instead, they made them totally unrelated, and then the reciprocals use the word secant. So I'm not sure the history behind that. It's not intuitive. It makes it a little harder to learn, so then I focus on the co to help me remember whether cosecant or secant goes with sine and cosine, because those are the 2 that are easy to get confused. But if you remember SOHCAHTOA, that can help you determine the ratio. And then as long as you know which one is the reciprocal, that can allow you to get cosecant, secant, and cotangent. But you guys are also free on your notes and quizzes and all that kind of stuff. You have your notes. You can have the sheet, so you don't really have to memorize it. But you will be doing these enough when you get into calculus. And there are some, if you're in engineering, there are some engineering courses where you use trig functions. So you may just end up memorizing these anyway. So I've got a right triangle here, and we're going to find the exact values of the 6 trigonometric functions of the angle theta. So in order to find all 6, we need to first get the missing side. And so we have to do that with the Pythagorean theorem. So just to review, the Pythagorean theorem is a squared plus b squared equals c squared. So a, b, and then c is the hypotenuse. So we're going to plug in our numbers, and basically the missing side is the adjacent side, or a. So we need to use the Pythagorean theorem to solve for a. So I've got a squared plus 5 squared equals 13 squared. So that's a squared plus 25 equals 169. And then 169 minus 25 is 144. And when you take the square root, that gives you a side length of 12. So our missing side is 12. So I'm going to go label that on our triangle. So once you have your complete triangle, all the sides labeled, then we can use the sides to basically find sine, cosine, and tangent. And we're going to do those main three first, and then you just essentially take the reciprocal to find the other three. So I'm going to start with sine. So sine is opposite over adjacent. So I'm going to just write opposite over hypotenuse. TOA. Make sure that I actually match what I meant. So sine is opposite over hypotenuse. So the opposite is 5 because that's across from the angle. And then hypotenuse is 13. So the sine is 5 over 13. And we don't have to get the exact decimal number, and we're not actually looking for what the angle is. We're just wondering what is the trig value at that angle. And so that is 5 over 13. And if we want to do the reciprocal right away, the reciprocal of sine is cosecant. So the cosecant of theta is just literally 13 over 5 because those are reciprocals. The next trig function is cosine. So we have cosine of theta. And cosine is ca, so that's going to be the adjacent here, which is 12 over the hypotenuse, which is 13. So that gives us 12 over 13. And then the reciprocal of cosine is secant. So secant theta is 13 over 12. And then the last one is tangent, which is tan theta. And that's TOA, opposite over adjacent. So that's the opposite is 5, and then the adjacent is 12. So that's going to be 5 over 12. And then the opposite of tangent is cotangent, the reciprocal of tangent, I should say. So that is 12 over 5. So as long as you have the right triangle, you can get all 6 trig functions, their values. Now, it does matter where you label theta. So in this example, we are told which angle that we're looking for. If we did the other angle, these values would be different. The sine of the other angle is different than the sine of the angle that we are given. And we never do the sine of the right angle, essentially, in a right triangle. We'll do like sine of 90 degrees when we're in terms of like unit circles, but if you're doing it in terms of a triangle, we don't really use that angle. We use the 2 acute angles that we have in the triangle. And so it's important to see which one is labeled because that determines what your opposite, your adjacent, and what your hypotenuse doesn't change for both of them, but it does determine which one's opposite and which one is adjacent. Are there any questions on this example? Okay. So my next one here, sketch a right triangle corresponding to the trig function of the acute angle. And acute are the skinny angles. Obtuse are ones that are greater than 90 degrees, so acute are less than 90 degrees. Then find the exact values of the other 5 trig functions. So here we're not given the right triangle, so we need to draw our right triangle. And so it doesn't have to be perfect or to scale or anything like that. So I'm just drawing a triangle. And just by default, I always label that angle on the left as theta. You can draw your right triangle as a mirror image of this. It doesn't really matter where you label your own triangle as long as you're consistent with your opposites, adjacents, and so on. So I've drawn my triangle, and we're given that the sine is equal to 15 over 17. So sine is so that's opposite over hypotenuse. So that tells us that our hypotenuse is 17 and the opposite side is 15. So we can use that to determine 2 of our sides of the triangle, and then we can use the Pythagorean theorem to determine the third side. So that's a squared plus b squared equals c squared. Again, we're looking for a squared plus 15 squared equals 17 squared. A squared, 225, and then I don't know what 17 squared is. That's one I don't have memorized. 289. So we subtract 225, we get a squared equals 64, which means that our missing side is 8. So I can label that on my triangle. Now, once I have my triangle, again, we're just going to find the other 5 trig functions. We don't need to find 6 because one of them is already given to us. We know sine, the opposite of the reciprocal of sine is cosecant, so I can immediately get that one just by taking the reciprocal. So that's 17 over 15. Cosine is ca adjacent, which is 8, over hypotenuse, which is 17. And then the reciprocal of cosine is secant. So the secant of theta is 17 over 8. And then we have tangent of theta, which is TOA. So that's opposite, which is 15 over adjacent, which is 8. And then the reciprocal is cotangent. So that is 8 over 15. So once you have that right triangle, and as long as you have that sheet ahead of you that shows where you plug in every number, if you have that sheet next to you, it's just a matter of plugging in numbers. Drawing the triangle, it doesn't really matter as long as you're consistent with your labeling, and that's the labeling that you follow for the whole time. Any questions? Okay. So we do have 2 special triangles that we use, and they come up a lot in trigonometry. These show up on the unit circle, and these are usually the angles that we have on the unit circle labeled, and so it's important to know what these triangles are and how you can use them to figure out the common trig functions. And so the first one is the 45, 45, 90 triangle, where it's basically, why am I blanking on the word where you've got the 2 sides that are the same? I think it's isosceles. I think that's the word that I'm looking for here. I haven't had to do geometry in quite a while. But we've got the opposite and the adjacent sides are equal, and then the hypotenuse is the square root of 2. And in my video where I connect the right triangle to the unit circle, you'll see why we have labeled it this way. But this is our 45, 45, 90 triangle. And so then the only really angle of any importance here is 45 degrees. And then we can use SOHCAHTOA to determine the missing parts. So we've got, I'm going to once again write SOHCAHTOA. So sine is opposite over hypotenuse. So the sine of 45 degrees, and it doesn't matter which one's opposite or adjacent because they're exactly the same, is 1 over the square root of 2. Now, we don't keep it in that form because we don't want to have square roots in the denominator, so we're going to rationalize the denominator by multiplying the top and the bottom by square root of 2. So that will get rid of the square root of 2 in our denominator. And so the sine of 45 degrees is the square root of 2 over 2. So that's one of the common angles that you want to memorize, or at least have a sheet handy with these because it does come up a lot. So sine of 45 is square root of 2 over 2. And cosine is actually the same value because the opposite and the adjacent are exactly the same values. So sine and cosine of the 45, 45, 90 triangle are identical. And that's why it doesn't really matter which angle you're talking about, because sine and cosine, you'll get the same value. And then tangent is TOA, opposite over adjacent, and both of those are 1, so the tangent is just equal to 1. So these are 3 very common trig angles that you see a lot, and so it's worth having them written down somewhere or memorizing them or just have some way to access them because you're going to see 45 degrees a lot. And sometimes we see it in radian mode, and 45 degrees is equal to pi over 4 radians. So if you see like the sine or cosine of pi over 4, that is 45 degrees. And so you want to also have those interchange or know what your angles and your radians are, how they interact, and their equivalency, so that way you can pull the right numbers. Now the next one that we have is the 30, 60, 90 triangle. And so again, we've got our 2 sides. This actually might be a true isosceles triangle, I think. No, it's equilateral because the large one that I have here is equilateral. You can see if I fill it in. So this is an equilateral triangle, and our 30, 60, 90 is basically taking half of that. And that's where you get the 30 degrees. So to determine the lengths of our sides here, the hypotenuse is 2. And then if it's equilateral, everything's 2. So that bottom side here, you cut it in half, you have 1. And then we use the Pythagorean theorem to get a length of square root of 3 for that height there in the middle. So the 30, 60, 90 triangle, it depends, your sine, cosine, and tangent depend on what your actual angles are, because that changes what is opposite and what is adjacent. So again, I'm going to just label it here. So TOA, just as a reminder. And let's start with our 30 degrees. So we're going to look at this angle right here because we need to know which angle we're looking at so we know what opposite and hypotenuse are and all that kind of stuff. So the sine of 30 degrees is so opposite over adjacent. So the side that's opposite 30 degrees is 1. I keep saying opposite over adjacent. I mean opposite over hypotenuse. I'm sorry, guys. Like, I keep using the wrong word, but I know what I mean in my head. So sine is opposite over hypotenuse. The opposite is 1. And then the hypotenuse of our triangle is 2. So the sine of 30 degrees is equal to 1/2. Cosine of 30 degrees. So that's cos. So that's our adjacent. And our adjacent side to 30 degrees is the square root of 3. And then our hypotenuse is 2. So cosine of 30 degrees is square root of 3 over 2. Then we have tangent of 30 degrees. So that's TOA, so that's opposite, which is 1, and adjacent, which is square root of 3. Now we don't want to leave that square root in the denominator, so we are going to rationalize it by multiplying the top and the bottom by the square root of 3. And this gives us the square root of 3 over 3. So tangent of 30 degrees is equal to square root of 3 over 3. So now let's look at it from the other angle, the 60-degree angle. So sine of 60 degree, in this case, opposite is the square root of 3, and then the hypotenuse is still 2. So you can see that the sine of 60 degrees is the same as a cosine of 30 degrees. Cosine of 60 degrees. So cosine is adjacent, which is 1, and then our hypotenuse is 2. So you can see that the cosine of 60 degrees is equal to the sine of 30 degrees. So sine and cosine here are exactly the same if the angles are complementary. They add up to 90 degrees. So sine of 30 is the same as cosine of 60. 30 plus 60 is 90. And so those are essentially equivalent trig functions here. And then tangent in 60 degrees. So our opposite is the square root of 3. And our adjacent is 1. So tangent of 60 degrees is just square root of 3. And it actually ends up being the reciprocal of tangent of 30 degrees. So if we're looking at tangent and cotangent, those are equivalent as far as complementary angles go, because the cotangent of 30 degrees will give you the exact same thing as the tangent of 60 degrees. So that thinking may be why we have sine and cosine labeled the way that we do, because then tangent and cotangent form equivalencies for complementary angles, but it is a little confusing, the labeling. But that's how that works, and you can see it work out with the 30, 60, 90 triangle, how these different angles in the same triangle can produce the same value. It just depends on where you're at. So that's good for reference. And so now we're just going to be given one of these triangles. And here, this happens to be a 30-degree angle. And we are going to find the exact values of the indicated variables. So here, I need to use that 30 degrees. And the only side that I'm given, which is 30, and I need to find R and X. And to do this, we are going to be using our values that we found right here. So let's start with finding R. So R is our hypotenuse, and we want to use our known side and our known angle. So this would be the opposite side from the angle and then our hypotenuse. So opposite and hypotenuse is sine. So the sine of 30 degrees is opposite, which is 30, over the hypotenuse, which is R. So now I have an equation here, and I can solve for R by multiplying both sides by R. So I have R times the sine of 30 degrees equals 30. And it's very important to put that degree symbol there for the 30 degrees, because if you do not have that symbol, it's assumed that it's radians. So in order to make it clear that you're working with degrees, you do need to include that degree symbol. And then if I divide both sides by sine of 30 degrees, we get 30 over sine of 30 degrees. So I can go back to my chart here. The sine of 30 degrees is equal to 1/2. So I can replace sine of 30 degrees with 1/2. So that would give me 30 over 1/2. And 30 divided by 1/2 is the same as 30 times 2. And so that side length r is equal to 60. So having that right triangle, the special right triangle is handy. You can use that if you have other lengths and you know one of the angles. So once you know r, then we need to find x. So we can find x by using the Pythagorean theorem because we know two other sides, or we can use the trig function to find x the same way that we did here. And that's what I'm going to do just to show you more practice of doing that. So in this case, we have the adjacent side and we have an opposite side, so we would use tangent to try to find x here. So we would have the tangent of 30 degrees is TOA, so that's opposite over adjacent. So that's going to be 30 over x. If I wanted to, I could do cosine with my known side that I solved for r, and I could also find x that way. But I try not to use values that I've already solved for in case you end up with something that you have to round, because then it makes your other values wrong. So I try to use only the values that I was given as much as possible to avoid any errors in rounding. So that's why I'm doing tangent here and not using the r that I just solved for. So we're solving for x. I can multiply both sides by x. So that's x times the tangent of 30 degrees equals 30. And then when you divide both sides by x, by tangent, not by x, you get 30 over tangent of 30 degrees. And then we're going to plug in what the value is for tangent of 30 degrees. So tangent of 30 degrees is square root of 3 over 3. So square root of 3 over 3. And we're dividing by a fraction. That's the same thing as multiplying by the reciprocal. So that's the same thing as multiplying by 3 over the square root of 3. And so that's 30 times 3, and then 1 times the square root of 3. So we get 90 over the square root of 3. But then we don't want to have a square root in the denominator, so we need to rationalize. So we need to multiply by the square root of 3 on the top and the bottom. So that gives us 90 times the square root of 3 over 3. And then 90 divided by 3 is, 30. And so we get 30 times the square root of 3. And so now we have found both r and x. And you may have noticed for finding x, it would have actually been quicker if I had used the original way that I wrote tangent of 30 degrees rather than the rationalized way. We would have had fewer steps, but you get the same answer either way. So it doesn't matter which form you use when you're solving this, your final answer will be the same. Are there any questions? Okay. So as I mentioned before about complementary angles, and I just want to point out that it's spelled with an E there because I was originally spelling it with an I, like the word complement, and that is not the same word. And I didn't realize that, and then I looked in the book, and I'm like, I'm not spelling these the same words. So it's an E there. Pronounced basically the same thing. So complementary angles add up to 90 degrees. And so we have co-functions of complementary angles. And so those functions that kind of go together, like I said, that sine and cosine, that's where they get co-functions, those are equal if they're complementary angles. So like I pointed out earlier, sine of 30 degrees is equal to the cosine of 60 degrees. And so we've got this chart here basically showing, and it's the way the formula works is that it's 90 degrees minus the angle, but you can also do angle minus 90 degrees. Either way, but it's just showing you those equivalencies. So I talked about how tangent of 30 is equal to cotangent of 60, so that's here on the list. And we talked about sine and cosine and their equivalencies between 30 degrees and 60 degrees. But the bottom row here, cotangent and tangent, you can see secant and cosecant also have equivalencies. And it's all, the angles have to add up to 90 degrees basically for you to be able to switch from one function to the other. What's nice is with sine and cosine, it's really easy to do because they're 45 degrees. And so that's why you can see that according to our formula here, sine and cosine are exactly the same because they are, or sine and cosine of 45 degrees are the same because 45 plus 45 is 90. They're complementary angles. So sometimes if you're given a value and you're like, oh man, I don't know what the, sine or cosine is, and it's like 120 degrees, you can then try to figure out, okay, what would be that missing degree, figure out the complementary angles. And in that case, we sort of use the reference angle first. We'd subtract 90, and then you can use complementary angles as needed to find these things. But just more rules for your toolkit when you're trying to find angles here. Usually I don't use these too much when I'm doing stuff with trig. So they're used more if you have to do anything like where you're converting from one angle to another. The last time that I had to use these formulas was actually in circuit analysis. So I haven't had to use it in anything like computer science related, but for those that are going into engineering in the circuit analysis class, there are some times where you need to kind of convert between angles like this. So just kind of keep that in your toolkit. So we also have trig identities. So those reciprocals that I mentioned before, like cosecant, secant, those are considered identities. And so you can even do reciprocals, like sine is the reciprocal of cosecant, that sort of thing. So those are just identities, just rules. We have quotient identities. So tangent is equal to sine over cosine. Cotangent is cosine over sine. And then we have Pythagorean identities. And so sine squared plus cosine squared equals 1. 1 plus tangent squared equals secant squared. And 1 plus cotangent squared equals cosecant squared. So these are all handy to have written down. The ones that I use the most frequently are the reciprocal identities, particularly out of the quotient identities, tangent 1, and then the sine squared plus cosine squared equals 1. And where those derive makes more sense when you look at it in terms of the unit circle. I think in one of my videos where I talk about the unit circle, I kind of explain where those come from, and it makes sense when you look at it in terms of that way. But those are important trig identities to have written down, because sometimes if you have a trig function in one form and you don't know what to do with it, converting it to another form might make it easier to work with. You might have, particularly when you go into calculus and you have to do derivatives or integrals, sometimes it's a lot easier to write it in a different form because then it's easier to work with. So good for your toolkit, your algebra toolkit, for when you go on to future courses, essentially. So now we're going to just do some practice here. We're going to use the given function values. So we're given the sine of 30 degrees is 1/2 and tangent of 30 degrees, which is square root of 3 over 3. It's the same ones that we saw in the 30, 60, 90 triangle. And we're going to use the trig identities to find the exact value of each of the indicated trig functions. So I could draw my triangle to do these and use the triangle to determine all of these, but we're going to practice by using the trig identities instead of drawing the right triangle, filling in the sides, and going from there. So we will start with cosecant of 30 degrees. So cosecant is the reciprocal of sine. So that's 1 over the sine of 30 degrees. So if it's the reciprocal of sine, and sine is 1/2, then this is going to be equal to 2 over 1, or just 2. Cotangent 30 degrees is the reciprocal of tangent. So that's 1 over tangent of 30 degrees. So tangent is square root of 3 over 3. This would be 3 over the square root of 3. And then we'd have to rationalize the denominator. So we don't want to have that square root of 3 in the denominator. So that would give us 3 times the square root of 3 over 3, and we just get square root of 3. And we knew this already because we did the 30, 60, 90 triangle. I'm just showing how we're doing it with the information we're given and these trig identities. So cosine of 30 degrees. So we want to use a trig identity here if possible. And let's see, trying to be creative here. I'm trying to think how to do this with one of the trig identities, because they want us to only use sine and tangent here. This is sort of the exercise, is to try to find these without using the other information. So to find cosine of 30 degrees, we're going to be a little creative. We're going to use the identity that tangent is sine over cosine. So if you solve that for cosine, you get the cosine is equal to sine over tangent. So basically multiply both sides by cosine and then divide it by tangent. So we can use that trig identity, and then we can just use our numbers for sine and tangent to find the cosine of 30. This is probably the harder way to do it rather than just knowing the 30, 60, 90 triangle, but this shows you how you can use these trig identities. So cosine of 30 degrees will be the same, equal to sine of 30 degrees divided by tangent of 30 degrees. So that's 1/2 divided by the square root of 3 over 3. And so dividing a fraction is multiplying by the reciprocal. So that's 1/2 times 3 over the square root of 3. So we have 3 over 2 square roots of 3. And then we need to rationalize the denominator by multiplying by the square root of 3 on the top and the bottom. That gives us 3 times the square root of 3 over, and then square root of 3 times square root of 3 is 3. 3 times 2 is 6, which then we reduce the square root of 3 over 2. So a much longer way to do it, but does show how you can find the values using your trig identities versus going back to that right triangle. Though personally, I would have drawn the right triangle and found it straight from there. Now, the last one here, cotangent of 60 degrees. Here we're going to use the complementary angle in order to find the cotangent of 60 degrees, because that is the same as tangent of 30 degrees. And so that's simply square root of 3 over 3. Because those are co-functions, cotangent and tangent, and the angles add up to 90 degrees, so they are equivalent. Are there any questions? Okay. Now I have here some practices of using our trig identities, and this is a good practice in algebra because you're basically going to be solving and rearranging in those skills. It's a practice of understanding the trig identities, trying to use your creative thinking and problem solving to figure out how can I rewrite these things to simplify. Essentially, when you're given a problem like this where it says use trig identities to transform the left side into the right side, you're basically sort of doing a proof. You're proving that the left side equals the right side by following these existing rules. And this is good practice for if you have to go on to calculus, because learning how to rearrange things into an easier form, like seeing cosecant or cosine and secant and knowing that that's equivalent to 1 could simplify things, a lot down the road. Be like, oh, that's just 1. And so it's a good skill to have, a good practice. It really helps you kind of practice your thinking. So when I do problems like this, I try to convert anything that is not cosine or sine into something that's sine or cosine, whenever possible, because those are usually the most common. So here I have a secant, so I want to rewrite secant in a way that I'm either using sine or cosine. So secant is 1 over cosine. Those are reciprocal identities, so I'm going to rewrite that. So we have cosine of theta times, and then secant is 1 over cosine of theta. And you can see that basically if you multiply those, you get cosine of theta over cosine of theta, and anything over itself is equal to 1. And so that comes out to 1, and we've basically proven this statement. So all we needed to do was rewrite secant, and then you can see, oh, cosine cancels out, you're left with 1. So this is a pretty simple example, just using the reciprocal identity to show how these work out. Move on to a more complicated one here. So 1 plus cosine of theta times 1 minus cosine of theta equals sine squared theta. So you always work with the more complicated side here. So the more complicated side is the left. That would be a lot easier than trying to take the right side and turn it into the left. We're going to take the left and turn it into the right. So we're going to use algebra basically. I look at this and I think, well, I have something squared, so obviously I need to multiply, so I'm going to FOIL this out. So if we perform FOIL, because we have 2 binomials multiplied together, then we can see where we go from there. So FOIL first, 1 times 1. Then I've got the O for outside, 1 times negative cosine of theta, so that's minus cosine theta. And then the I in FOIL is inside, so that's cosine theta times 1, so that's plus cosine of theta. And then last, cosine theta times cosine theta. So that would be cosine theta squared, but the way that we do things with trig functions is we put the square on the cosine, not the theta, so that it doesn't look like you're squaring the angle. We're squaring cosine, not the angle. Yes, negative, thank you. I would have had a problem. I would have been like, wait, this is not canceling out. Yeah, negative cosine squared theta. Yeah, we don't want to go through the whole thing and then end up with a problem. So Our middle terms completely cancel out because we do have, this is it basically comes out to a square of a binomial, or a difference of two squares essentially, because those insides cancel. So the minus cosine theta plus cosine theta completely cancel. We have 1 minus cosine squared theta equals sine squared theta. So now from here, it's like, okay, well, what do we need to do? We need to somehow get rid of cosine and turn it into sine squared. So this is, we're using our trig identities. So I'm going to go back to our list. I would use the Pythagorean identity that we have that I've highlighted here. That's sine squared of theta plus cosine squared theta equals 1. And basically, if you rewrote that, if you solved it for cosine squared, that would be 1 minus sine squared theta. So we're going to take the Pythagorean identity there, solve it for cosine squared, and now I'm going to replace cosine squared with 1 minus sine squared theta. So I have 1 minus, and then cosine squared theta is 1 minus sine squared theta from that Pythagorean identity. Then that equals sine squared theta. So we end up with 1 minus 1, which is just 0, and then minus a minus is a positive, so we get sine squared theta equals sine squared theta. And so now we've just transformed the left side into the right side. Any questions on this one? Okay. This is my last one here. Here, instead of theta, we're using beta. So for angle measures, we usually use Greek letters. Theta is the most common one that we use, but alpha and beta are also used if we're not using theta. Then there's some other ones like phi that we use. There's other Greek symbols. We don't use pi because pi is part of radians, but beta is another option you use to indicate angles. So here we actually have beta. So it's like a fancy B with a little line. Once you start doing stuff with trig, you start to get really good at writing Greek letters because Greek letters come up a lot once we start getting into higher levels of math. You know, we've got the theta, we've got alpha, you've got beta, you've got pi. One Greek letter that I had to use in grad school, it's something that looks like that. I am not even sure how to, I just wrote a squiggle because I could not figure out how to write it. I think it's G or she, I don't even know how to pronounce it, but it's some Greek letter that has lots of squiggles that I had to use in grad school. So higher levels of math you get, the more you practice you get with Greek letters. But beta is pretty simple to write. So we want to turn the left side into the right side. And this one may have some more steps because it is looking a little more complicated. We have something with a fraction that now turns into a cosecant here. So first thing that I would do, if I've got these tangent and these cotangents, I would rewrite my cotangent as tangent. Cotangent is 1 over tangent. So that's the first thing that I would do so that I have everything that's sort of tangent there on the left, and then we can kind of see what we do with it from there. So, and I'm not sure how many steps this is going to end up doing. I wanted to wait to actually solve this one so that way I can show my thinking process as I solve it so that you guys can see that as well. So I don't know how many steps it's going to be. Specifically, it says transform the left into the right, so we don't want to do any rewriting of cosecant. That would be something that I might want to try, but not in this case because it says to only touch the left. So I'm going to start by just rewriting cotangent in terms of tangent. So I've got tangent of beta plus 1 over tangent of beta all over tangent of beta. And then that is equal to cosecant squared of beta. So looking at this, I need to somehow simplify the left side. And I think what makes sense to me is taking the top fraction and splitting it up, or taking basically the numerator on top, and we're going to create this two fractions from here. So we're going to take each part of the top and divide it by tangent of beta. So I'm sort of reversing what you do when you add fractions. So I can split this up to tangent of beta over a denominator of tangent of beta plus, and then I would have 1 over tangent of beta over tangent of beta, and that is equivalent to 1 over tangent squared of beta. Because we are dividing by tangent of beta, and then we divided it again. So that's dividing twice, or squaring that. So tangent of beta over tangent of beta, that is equivalent to 1. Now, I don't personally know of anything helpful with 1 over tangent of beta. If you go to our trig identity thing, we don't have anything where there's a 1 over tangent squared. But we do have 1 plus cotangent squared, and that's equal to cosecant squared. So it looks like we're getting to this last one here. So what I'm going to want to do is use our reciprocal identity, the fact that 1 over tangent is cotangent. So what that means is that 1 over tangent squared is equal to cotangent squared. The squareds are equivalent because the top is just 1. 1 squared is still 1. So this will be cotangent squared of beta equals cosecant squared of beta. And then going back, that gives me that bottom Pythagorean identity here. 1 plus cotangent of theta equals cosecant of theta. So we're going to use that Pythagorean identity to get cosecant of theta. So as I'm going through these, I'm kind of looking at the trig identities I have, and you kind of think about, well, where am I heading? What might be helpful to get there? So our final step here is just to use that trig identity, and we get cosecant squared of beta equals cosecant squared of beta. And so now we've got the left side equal to the right. We had to do a little bit of creativity. That first step, where I went from the first step to the second step, where I split up the fraction, an alternative would be to maybe multiply the top and the bottom by tangent squared, or by tangent, to try to eliminate the fraction on the top. There's lots of different ways that you could do a problem like this, and you can still end up at the same spot. It's just a matter of following the algebra, making sure you're doing substitutions correctly, making sure that you are multiplying things correctly, so that everything kind of cancels out the way that it needs to. Are there any questions? Okay, so that was the last example that I had for you guys. On the homework, you don't have to do any of these show trig identity kind of things. This is more of once you're going further down the road, these are good skills to have. But it's on the homework, what you will be doing is those problems where you had to find, where there was that triangle and it was like find the unknown side, find x, find r. That is something that's similar to a problem on your homework, so that part would be helpful. And then just knowing your trig functions. I do not have an example of question 1, but To do question 1, you're going to have to use unit conversions. And in the announcements, there is a video on showing work for unit conversions, because the most frequent thing I see is that people do not show the work properly, and what they write down, if you follow units, is not correct. So I usually end up having people lose a lot of points on that one. You have to do unit conversions. You're going to be dealing with angular, well, you can do it multiple ways. Some people use angular velocity or speed on that one. Some use the arc length on that one. And for question 1, you want to think about number of revolutions. As my pedal goes this way, what is it connected to? For every turn of the pedal, how many turns is it for the sprocket, and then how many turns is it for the wheel? So you want to think about that. And you do need to show all of those calculations and explain where your numbers come from. If you just write down a whole bunch of numbers with like no units, it just looks like a mishmash to me. That's the one problem where a lot of people lose points, not because they're wrong, but because they've written down so little work that it's just random numbers all over the page. And I know what they're doing, because I know what the problem is. But if somebody else is looking at that, they wouldn't be able to follow it. And so it's important to make sure that your work is followable by anyone. So you really need to make sure you're labeling all of your units, explaining where numbers come from. You can't just pull numbers out of nowhere to get full credit on that one. So it shouldn't just be like a mix of random numbers multiplied together, which is frequently what I get and not mathematically clear. Watching my videos on like section 4.1 might help for that one. And I think that's the hardest. I think that one, and then question 2 is usually a little tricky for people. Question 2, it's all about drawing the picture to help you figure out that one. If you don't draw a picture, you usually find the wrong part. So drawing a picture is key, especially for anything trig. Basically, anything that involves trig, I always draw a picture, because otherwise I'm likely to mess something up. Any other questions? Mechanism means the arm minus the wiper. Yes. Yeah. So on question 2, you've got the arm thing. The wiper is on the upper part, and then the mechanism is like the lower part. That's what it's calling, the mechanism. And then the whole thing is the arm. So yeah, it's like a real wiper. Exactly. Yeah. So that's important to know, because if you have the wrong parts labeled, which is another thing that I've seen, is people label the wrong part of the wiper, the wrong numbers, and then it messes things up. So just be very careful on that one. Anything else? All right. Thank you, guys. I'm glad that I ended up with 3. Steven looked like he was popping in and out. He might have been having connection problems, but glad that you guys were able to attend, especially on a Saturday. My Saturday's been, well, it's been basically rainy, so it's like, not really doing anything fun, not really doing anything outside. But thank you guys for attending. I'm going to try to, depending on how fast this recording kind of goes through, I may email